Hi, so today we'll be discussing this paper, FrugalGPT, which is about how to use LLMs in a cheaper way while maybe retaining the performance or maybe even improving the performance in some cases. It's a pretty cool paper. So, from the abstract itself, they say that they outline and discuss three different types of strategies. So, first of all, what is the motivation of the paper? Using LLMs is expensive. So most LLMs are paid and querying them infers a fee. And this fee can be prohibitively expensive for small companies, small businesses, or even for large companies which have a very high request rate. So we need to figure out a way to make them cheaper. And they say that there are discuss three types of strategies for that: prompt adaptation, LLM approximation, and LLM cascade. Especially in their approach, FrugalGPT, they use LLM cascade, which is nothing but like using a combination of LLMs for different queries to reduce the cost and improve the accuracy. What it means is that if you have a particular query, Q1, and you have different models M1, M2, M3, or whatever, and each of them has a different cost. Maybe an M1 is very cheap and M3 is very expensive and M2 goes somewhere in the middle. So what this model will do is that it will first send this to M1, which is the cheapest version. It will have some way to identify, okay, is the answer from M1 good enough? If it is good enough, it will take this. Otherwise, it will send the query to M2. And similarly, if the answer from M2 is good enough, it will take it. Otherwise, it will send it to M3. So in the best case, you will be only querying the cheapest LLM. In the worst case, you will be querying all three LLMs. But they show that in most cases, uh, you can get a lot of cost savings from this. And in fact, they say that on a particular data set, uh, they achieve accuracy similar to the best LLM, which is GPT-4, with 98% cost reduction. So their cost is like they have a cost reduction of 98%. So probably their cost is like 2% of the original of using GPT-4. So yeah. Uh, so yeah, here they mention that say using GPT-4 for a small business might cost over 21K. And like how do they calculate this cost? So the cost of using an LLM usually has three components. The prompt cost, which is a cost proportional to the input, the generation cost, which is the proportional to the output's length, and sometimes a fixed cost. So if you have a model and you give a query uh, x1, x2, x3, xn, where these are tokens, and you get an output y1, y2, y3, ym. Usually the price of LLMs is a function of n comma m plus c is what they mean. Or more like it is actually more like a function of n plus a function of m plus a constant. This is our dollars cost equals to. So, and this is usually linear. So twice the amount of prompt tokens will incur twice a cost, something like that. Uh, so yeah, this is the cost associated with LLMs, and also LLMs have very different amounts of costs, sometimes even differing by two orders of magnitudes. So so for 10 million tokens, GPT-4 might cost $30, whereas this other model might just cost $0.2. So yeah, I mean it their cost differs a lot, and for particular use cases, their accuracy might not differ proportionately, and you might get some cost savings or some significant cost savings out of it. Which is what they say that if the tasks are relatively simple, then aggregating multiple responses from a smaller model gets a better performance. However, for more difficult tasks, you might actually need more larger models. So that is one thing which I think about this paper, that this might not, like this cascading approach might not work very well for very hard tasks, in which case it might always like lead to querying the hardest, like the biggest model itself. But for relatively easier tasks, this might be a better approach. Also, they say that this is also useful because if you only depend on one API, then if that API is down, you might experience severe issues. But if you have a cascade of multiple APIs, you can still get a result if one or two of them goes down. Okay, first, one thing which I would like to do is to look at how they got this number, 21,000, which gives us a sense of how to like price these LLMs. So this is how they calculate it. So say they take a hypothetical example. So let us say we are using GPT-4 and we have 36,000. Suppose we have 36,000 queries per month, and for each query, the input is around 1800 tokens and the output is around 80 tokens. And the input costs and output costs for GPT are 0.03 and 0.06 per thousand tokens. So this is another thing to note, that the input and output costs are asymmetric usually, because there's a different, they mean different things actually. So for outputting a token, you might have to like outputting is generation is going to be more expensive, because when you are using an LLM, it is usually it multiple times it is auto regressive, and you have to like run the mod. So like you'll get one output and then you'll feed this back to the model and you'll get another output. So it involves multiple outputs, multiple number of passes through the model. I mean, they can be produced sequentially. I don't know. They can be produced parallelly also, but not really, not always. So yeah, output is the. I mean, the output cost is definitely going to be more than the input cost per token. But say if this is the cost, then for 80 tokens, for 80 output tokens, this is the cost. For 1800 input tokens, this is the cost, and this is the total cost you get if you have 360,000 queries. So this is one simple way in which you can like calculate the costs of using a model. Okay. Okay, so here you can see an overall overview of the paper and its results. So what this says that uh, existing LLMs are just simple. You have a particular LLM, you give it a query, you get an answer. What this says that you can make it cheaper. You can have a budget, and you can make it cheaper by using these three techniques: LLM cascade, approximation, and prompt adaptation, and also like being smart about your prompting strategies. Also in this paper, they only focus on LLM cascade, and this is the performance versus cost benefits that they get. So the y-axis shows the performance accuracy, and the x-axis shows the cost. The red line is FrugalGPT. So this is GPT-4. So it almost reaches GPT-4 level performance on something a very less budget, a very less budget, and that is what their paper is mostly about, like how to get a similar or even higher performance than the best LLM out there on a particular task, uh, in a much cheaper way. I do have to stress that this is on a particular task. I don't think there is a way they can beat GPT-4 on all tasks because it is just crazily good. That is the advantage of big models. They are crazily good at a lot of things. But on a specific task, these things might work better. So, what tasks do they consider? They consider query answering, which is basically you are given a query and you have to give an answer based on that. And maybe if I go to the data set which they used, will become more obvious. So yeah, in their particular case, they look into these three data sets: headlines, overruling, and co- COCA. So in headlines, you have it is a financial data set in which you get a news title and have to determine whether the price of gold will go up or down. And if we look for an example, yeah, something like this. Gold of the lows after decimal US GDP data. Would the price go up or down? This is what the model has to predict. So this is one of the data sets which they use. This is a very simple task, actually. I mean, I don't think you actually need an LLM for this. This is a very simple task, and which this is one of my criticism of the paper. The tasks which they have compared on are very simple. So yeah, that is one criticism for the paper. But yeah, to keep in mind that is the kind of tasks they are considering. Obviously, their approach can be used in different problem statements also, but then the uh, com like the cost versus performance comparisons might be different, is what I think. But they say that there. Okay, let's go into the three strategies which they proposed. So prompt adaptation. So given that the costs are dependent on the size of the input prompt, a logical approach would be to reduce the length of the input prompt. One method to do that is prompt selection. And so usually when you train this, when you uh, in the prompt, you have a bunch of examples for in context learning. So if you are solving, say, the new financial news task, you might give a 4 or 5 titles and their predictions in the prompt itself for the model to perform better. What they say is that the prompt selector might, so if you have, initially if you were giving like 4 examples, the prompt selector might only select these that, okay, these 2 examples are what we actually need to give. We can actually get away without using the other 2 examples. And this might depend on the query itself. Like for a different query, we might need first and fourth. For a different query, we might need second and third. But essentially, you can reduce the number of in-context examples you have and reduce your cost. The other is query concatenation. So instead of like, if you have multiple queries, then instead of like passing each query individually, you can uh, modify the prompt in such a way that you can pass both, say, 2 queries together, and you can ask the model to give an output for both of them. And these models are able to do this. So you'll almost have a 2x reduction in your cost by using a very simple thing like this. Uh, Obviously, the performance might take a hit, but it might be worth it. The other thing might be uh, LLM approximation. So basically, you're trying to approximate your model with a different model. Also, what they say is that you don't really need a model always. You can just cache your results. So they talk about a completion cache, and in which the idea is to store responses locally in a cache when submitting a query to an LLM API. So when we get a new query, we see if a similar query has been previously answered. If so, then we just result the data in the cache, and otherwise we have to like requery the model. And this is very useful for search engines which are powered by an LLM because different users might search for similar keywords, and you might just return it from the cache. So you have a cache, and this is the query. If a similar query, say q dash, was there in the query itself, you can if the queries are similar, you can just output the result of q dash uh, instead of q, and you can like save on costs. The other is fine tuning. You can fine tune a smaller model, so you can use the bigger model to generate some training data and then use it to fine tune a smaller model, which might be cheaper. You need this bigger data because you might not have the labels actually. So say you can say you have an input task and you don't really have a you have a label for 5 examples, but 5 examples are not enough to fine tune the model. You can pass say 100 examples through a bigger model, say like GPT-4, get the outputs, and then use those 100 outputs to fine tune your smaller model. So it at least approximates the results of the larger model. So you can get some cost savings based on that also, because the smaller model might be cheaper to run. And the third one is LLM cascade, which is what I discussed previously, that you have an input, you have multiple LLMs. First, you pass it through the smallest LLM, you get an output. If you are confident enough that if you are not confident that the output is correct, you pass it through the bigger model. And if you are confident that the uh, output is correct, then you accept that answer and you don't pass it to the next LLM. So you can have a series of LLMs, and based on the, I mean, for different calls, you will have, if you are lucky, you might get away with calling just the smallest LLM and have a lot of cost savings. If you're unlucky, you might have to run all LLMs and your cost might increase. But overall, they say that this approach helps you reduce the cost a lot. And this is the approach that they consider. Now they gave a very mathematical formulation of this, which I'll skip because they did not go into the detail of how they solved that. So they say that you basically need two things for their approach. First, you need a scoring function which tells you how good the answer is at each step. You have a scoring function which says how good your answer is, and based on that you go to the next step. And they say that this scoring function can be a simple regression model. And okay, I have a doubt. Like I do not totally understand. Like if you have this, I mean, okay, given an answer, telling if it is correct or not may actually be an easier task than like generating the answer. So I think it is fair enough in that sense. Because say if you want to generate, if we translate this division, if you want to generate the image of a cat, generating the image of a cat is hard, but telling, like creating a classifier for an image that an image is a cat or not is relatively easier. So yeah, for generation tasks this might be good, but for classification tasks this is not that good, right? Because uh, uh, if your output is yes or no, which is the output in their case, and you have a query and you have a scoring function which says that okay, Q1 yes has a score of say 90%, and you will use this score only to decide whether to take this label, then why even run this through the model? Like why not just have query one and a yes, pass it through this regression model, get 90% or whatever, and just use this as the classifier or something. So for generation tasks, this might be better. For classification tasks, this approach, if you have such a model, then you might just as well use that model, is what I feel. But anyway, and the other is an LLM router. The LLM router selects which APIs to use. So they say that theoretically, they say that if you have like hundreds of APIs, you might want to select just like say 5 APIs out of it, and they have an LLM router for it, and they have some mathematical formulation for that, like how to train this. But in their experiments, they only have actually 3 LLMs. So since they only have 3 LLMs, I don't see the point of that because they only have 3 LLMs. Also, like deciding which LLM to use first and which LLM to use next can be done by this, but I think all like just going from the cheapest to the largest might also work better. But anyway, they also don't like really delve into the details of how they do this, because they say that we develop a specialized optimizer which prunes the search space of L by ignoring any list of LLMs with a small answer to disagreement, then approximate the objective. But I did not like find any details of this. Maybe there's an appendix which I'm missing. I downloaded this from archive, which does not have an appendix, but maybe there's an appendix. Anyway, now off for some results. So this is the datasets we use. Now, particularly for headlines dataset, uh, what their strategy turned out to be was this. Like, this is automatically discovered. They did not like find like hard code this. So first, the model goes to the smallest and cheapest model, and if the score is less than 0.96, they call the next model, and if the score of the next model is less than 0.67, they call the next model. Otherwise, they don't call the next model and just get the output from the previous models. And they say find out that they can beat GPT-4 by only a fraction of the cost, which is awesome. And then they say get a bit into like why does their approach work, and basically it is about LLM diversities. And what they mean is that even an inexpensive LLM can sometimes give correct answers. So like GPT-4 might be great, but other models also might work for some cases. So if you can like use them for those cases and use the larger model for the other cases, then you can have some uh, gains. They have this metric called MPI, maximum performance improvement. Also, I did not really see the point of it, but what it says overall is that the MPI of A, LLMA with respect to B, is the probability that A generates the correct answer while B generates the incorrect answer. It is essentially a maximum performance gain achievable by invoking A in addition to B. So it is basically like you have two models, A and B. Uh, what is the percentage of times where B gives the wrong answer and A gives the correct answer? Say that is 50% of the times. So you can have this much gain if you call both A and B. So that when B fails, you can like get the correct answer from A. That is somewhat what this metric wants to discover, and they created a plot from it, and they showcase that okay, it is not as if like GPT-4 is the best model. There are some cases where the other models are able to complement it, and you should leverage it for those cases to get these cost savings. So yeah. Also, another interesting point they raise is that the cost ranking of different LLM APIs is not fixed. So for different datasets, different LLMs might be more expensive. This is because their input and output pricings can be different. So they say that J1 is the second most expensive on headlines, while GPT-3 is the second most expensive on the other two datasets. And this is because J1 has a high cost for output tokens, but it charges nothing for input tokens, whereas GPT charges for both input and output tokens. Since these models have a different like input and output costs on different datasets, one of them might be cheaper and one of them might be more expensive. So this is actually a good detail which I thought. So when you have like for your task, you can see different models. They might surprise you on how the cost is actually structured. I actually looked to a presentation. I saw a presentation which went into much more detail into this, not from FrugalGPT, from a different company which I forgot the name of. Okay. Uh, Also, they say that sometimes more expensive LLMs can result in worse performance. So yeah, do use, uh, do give the inexpensive LLMs a try before you settle on GPT-4. Also, they admit that their approach is not perfect because in the worst case scenario, your model might have to make like 3 queries, so it might have to query all of them, and that will lead to more costs than less costs. But they say that that happens rarely, and that is why they do have these savings. However, I feel that this is the case for very simple tasks, and for very hard tasks, uh, the simpler models might not work, and they might always lead to all the models being called. I would hope that they'll like I, that might not be the case as well, but they need to test this on a much harder task before we can comment anything. Maybe they have. This came a few. This came sometime back. It might have already. They might have already worked on that. But yeah, overall, I think this is a very cool paper, and I like such kind of papers which like consider the costs of things, like how to make models cheaper and faster, more easy to use. Because like even if I want to use these for anything, then uh, it is prohibitively expensive for me right now. So if such things can be done, it might become easy for s- uh, people who don't have a very high budget to even use these models. So yeah, overall it's a very cool paper. And yeah, thanks for watching.